Hi, I'm Ken McKenzie. I'm a student at the University of Wisconsin-Milwaukee, and today we're going to be exploring how modern computer systems actually work behind the scenes. And we're going to be focusing on something that's known as the client-server model. And even if you're not familiar with that term, we all interact with these systems every day. So every time you check your email, stream a video, share a file online, these things are going on in the background. So it's really kind of important to know about this kind of stuff. The goal of this presentation is to break down how these systems function in a clear and practical way. So we'll look at how data is stored and secured, how different systems communicate with one another, and how their parts communicate with each other, and then also how performance and reliability are maintained. So in talking about this, I'll use some examples along the way that are familiar to pretty much everyone. So things like online banking, as I said, file sharing, and then web applications. So like apps that you would download to your smartphone to provide some real world context for what I'm talking about. And by the end, you should have a pretty good understanding of how these client server systems operate and why they have become so prevalent in modern computing. So that's enough for the introduction. And now we're going to talk about the most important advantage of client server systems, which is security. Security is the single biggest advantage of a client server system. In a client server model, data is stored in a central server rather than being distributed or spread across multiple individual machines. And that design makes it much easier for system administrators to protect, monitor, and control access to sensitive information. So when you think about how authentication works, authentication is proving who you are to a system. So authorization is the determination of what access rights you have, and then authentication is proving who you are. So when you log into a system, your credentials are verified against a centralized database. And we'll talk in a later slide about why it's important that that centralized database never goes down or experiences an outage. Because, I mean, when you think about authentication, you want that something to always be online. And if the centralized database is experiencing an outage, then your credentials don't go through. But back to authentication. You log into a system, and that login process happens in one place when you're talking about a server. The login process is happening on the server. And because it's happening in one central place on the server, it's easier to enforce consistent rules. So a university system might allow students to access grades, and for professors to enter grades, and for administrators to access the records. And all three of those user groups would have their permissions controlled centrally with role-based access controls. And that reduces the risk of inconsistency or accidental access. And then, so we talked about a university server, and another example would be online banking. And your financial data isn't stored on your personal computer. That's too insecure. It's stored securely on the bank servers. And those servers apply the necessary encryption to keep the data private and keep it from becoming corrupted. And then the servers also monitor suspicious activity with logs, and system administrators monitor those logs for suspicious activity. And then, as I said, the access controls are enforced. The role-based access controls. So whether you're a user of the bank, or whether you're a database administrator of the bank, or whether you're a systems administrator at the bank, there are different role-based access controls for each of those user groups. And this centralized approach to having the data stored on the server and having each of those user groups access the data on that server from their own client computers is what makes online transactions secure and really viable as a business operation. And I should mention that there's an important trade-off. So centralization improves control, but it also concentrates risk. And that's we'll talk about this in the next slide. But if the server is compromised, the consequences can be really devastating and widespread. So if a central database is breached, attackers can gain access to the data of many users all at once. And you think about like what happened with Target and the millions of customer records that were inappropriately accessed, and Equifax or any of the other data breaches that happen, and that it's a huge reputational risk for a company. And that's the danger of having a central database that holds all of the records. And that is where system design becomes critical. And to reduce the risk of a data breach, organizations use multiple layers of protection. It's known as defense in depth. And those layers of protection can include encryption, access controls, network segmentation, and so on. And they can also replicate data across multiple servers. So no single point of failure exists, as we'll explore in the next video. And that's an effort to reduce the central point of failure through the building in of redundancy to the system. So the main takeaway from this slide is that client server systems don't automatically guarantee security, but they provide a structure that makes strong security possible if implemented thoughtfully. And the balance between control and risk is something that system designers always need to be looking out for and trying to ensure that the benefits of having the centralized server in terms of security are not outweighed by the risks that having one access point that a hacker can attempt to breach be exposed. So now moving on to the second slide. Sorry, that was a little long. I'll try to speed things up. To understand the risks of centralization, it's important to think of the server as kind of the brain of the whole system. And it handles tasks like storing data, as I said, authenticating, and generally controlling communication between the different parts of the system. And because so much depends on the server failure can have really widespread consequences. So if the server goes down, all the services it provides become unavailable. So if you think about like mail servers, that's kind of like the most easily accessible example, or most easily available example of what can happen in an outage. So if a Microsoft Exchange system server goes down, like entire companies lose their email access, and productivity decreases dramatically during those times as people don't have access to email, and businesses incur losses because of the loss of email access. So it's a real concern for the economy. And socially important that things like email servers don't go down and that we have reliable uptime. And then another example, in addition to mail systems, is authentication systems. So if the authentication server goes down, same thing. You're in the office at 9 a.m. on Monday, and you can't log in because the authentication server is down. your work time is now paid, but you're not doing anything. And again, that's a drain on productivity and a cost to the business. And then, I mean, another example that you could use is streaming platforms. And I mean, if the streaming platform is down, customers don't have access to the movies they want to watch, and they become dissatisfied with the service and churn. So again, it's a concern for the business. So in modern systems are rarely built to run a single server. So there's redundancy built into the network structure, and that's known as redundancy. And that um, and servers also serve more than one function usually. So another server can take over if one fails, and that's known as failover. So centralization improves efficiency, but it also creates dependency. And the efficiency comes from having the single access point, but that access point creates dependency because everything is dependent upon that central server functioning. Okay, slide 3. So now we've discussed the risks of server failure, and the next question is when backup systems become necessary. And the answer to that question is basically a cost benefit of the impact of the failure. So the greater cost, the greater impact, negative impact that not having a backup system would cause to the company in terms of lost data or customer churn or lower productivity. All of those things, if those costs are high, then organizations will more than likely opt to implement a backup system to protect against those potential loss cases. So, I mean, I mentioned the 9 a.m. Monday example of losing access to email or an authentication server, and those cause productivity loss. Or, I mean, the example of the streaming services losing access to the central server where that acts as a repository for all of the media. But the stakes are even higher in safety critical systems. So things like air traffic control or hospital systems. I mean, these are systems that really can't go down, and it's especially important to have failovers in those cases, or have redundancy, have backup systems in place so that air traffic control doesn't lose track of an airplane, or a patient record is not unavailable at the time of a surgery. And then I mentioned business continuity, and that kind of goes along with the previous things that I mentioned: productivity, customer churn, um, and impact to revenue in terms of the value of data and the availability of data for analysis. Business continuity is kind of a longer term concern, and it probably is not going to affect a business that much if a backup system fails, unless it's a data breach. And in that case, it really could be devastating for a business. But the occasional outage of a server is not going to have implications for business continuity in most cases. But even so, I mean, as you see in the slide, if manufacturing downtime delays production, there are downstream cost of that. I mean, the distributor is unhappy, the retailer is unhappy, the customer is unhappy, and that all, I mean, if manufacturing downtime delays production because of an outage, and that outage is recurrent, eventually the distributor, the retailer, the customer lose trust in that manufacturer, and that manufacturer could face business continuity issues as a supplier. So it is something that is feasible. Okay, so scalability refers to the ability of a system to handle an increased workload efficiently without losing performance or degrading. And it's basically about whether a system can grow in line with usage, with increased usage demands. So, I mean, one way of thinking about this is thinking about a restaurant. So, like, one cook is going to be enough if you have one person dining there, if you have 5 people dining there. But once you get to 10, you might need to hire another cook. And I mean, scalability is all about, well, how many cooks can we hire and not have the kitchen get too big? And then once we hit a certain number of customers, and we have enough cooks, do we renovate the kitchen and make it bigger so we can fit more cooks in there? Ideally, you don't want to have to renovate the kitchen. You want to have the kitchen big enough to accommodate the growth in the customer base you're expecting. That is essentially the question of scalability and trying to gauge, okay, upfront, this is what we're willing to pay on the kitchen in order to be able to handle expected growth and balance out that upfront cost with the potential to serve those additional customers without having to make expensive renovations later. You want to build the ability to grow into the system so that you don't have to completely rebuild the infrastructure. So like when Netflix created its streaming service, they had to run detailed analyses of how many customers they were expecting and what they expected the bandwidth to be in order to build out their network. And you don't want to build out the network too much, then you're spending assets unnecessarily. But you also do want to build out the network past what your current state of operation is to be able to accommodate your expected growth. And that's how you achieve scalability in your operations, is by looking at that gap between current customer base and expected customer base and the growth that represents that gap, and then looking at your capability gap and where are you today and where do you have to be in order to meet that expected customer base. And you're also doing the cost benefit analysis of how much do we have to spend in assets up front as opposed to how much will it take to retrofit later on. So, I mean, other examples in addition to the restaurant example that I mentioned earlier, I mean, or Netflix that I mentioned, Amazon has to account for peak shopping periods on like Black Friday and Cyber Monday. And they have to be able to scale their operations. And that's where you really hear all this talk about cloud computing coming in and being able to scale for peak loads by buying compute on servers owned by other people that are absorbing the fixed asset costs so you can treat them as variable costs. And that is a really powerful business model that these cloud computing companies have. And it's allowing a lot of flexibility to small and medium-sized businesses to not have to invest upfront in the fixed assets that having a server would entail, and being able to treat it as a variable cost that can be scaled up and down to meet demand. So it really is something that allows small and medium-sized businesses to become much more competitive than they otherwise would be. And cloud computing has been an absolute gain for society. Social media platforms are another example of entities that need to scale. So Facebook expects, I don't know, 5 billion users. Well, they're going to have to optimize their pages to meet those expectations of the future user base, and they're going to have to buy upfront through futures contracts bandwidth on the internet network. So I mean, it's just going. That's what they have to do in order to scale, and they'll contract for that bandwidth upfront with futures contracts with, like, I don't, AT&T, MCI, those kinds of companies, Comcast, the companies that own the fiber optic lines, and they'll contract with those companies upfront to the amount that they feel is a safe amount given the future growth they expect in their user base. And in that way, they're ensuring they remain scalable as their user base grows. And scalability is not only about users, though. I mean, it also could be about complexity. So if you take a manufacturing system, as production increases, the system has to track more inventory, manage more schedules, coordinate more processes, and any system that isn't scalable. So if your inventory tracking is not scalable, if it's not sufficiently automated, it can become a bottleneck in the process and slow things down. And I mean, the bottom line is that scalability is about planning for growth. That is the main takeaway here, is that you're planning for growth when you try to make your processes scalable. You're planning for growth when you build a restaurant that has a 2,000 square foot kitchen. I mean, that's a lot of cooks. Okay, so back-end processors. Back-end processors perform non-user facing computational tasks. So they're the thing that does the work behind the scenes. And users interact with the front end, and I mean, well, the front end, as we'll see in the next video, is more about communication. So this is not really like, when you're talking front end processing and back end processing, it's not the same as the distinction between front and back that exists when you're talking about web design and the division of the full stack. It's different. The front end processor, back end processor distinction is different than the distinction that exists in web design when subdividing the full stack. I found that to be confusing. So the back end handles tasks like processing data, executing application logic, interacting with databases. So those kinds of things that happen behind the scenes. And the back end interprets the actions that are communicated from the front end and performs the operations, the arithmetical operations on those transmitted tasks and resubmits them to the user. So the backend, so like user fills out a form and like backend checks form validation. Actually, form validation doesn't have to happen on the backend. It can happen on the client side. But let's just assume that JavaScript is not checking form validation and that it's on the backend processor side. So the backend processor is checking logic and then gives it the okay and sends that submission successful message back to the browser. So that is the backend performing a logic task. Now, that wouldn't happen in the real world because form validation, as I said, happens in the browser through JavaScript, but that's how it used to happen. So when you think about online shopping, the website is the front end. It's not the front end processor. The front end processor is a component in your computer that allows for communication. It's very confusing. The terminology is very confusing. Somebody has to do something about this. But the front end. What is a better way to say it? I don't even know. But the front end, your browser shows the web page with the different items available for purchase. So I said online shopping, it could be a movie theater that has seats or a sports stadium. And all of those seats have values assigned to them on the back end and are eligible for purchase. And the back end takes care of, okay, you selected the seat and you belong to this customer group. So this discount applies, and we're going to calculate the total, and we're going to store the total in our transaction database, and we're going to calculate the taxes based on the API to the current state tax rate, and we're going to return all of this to the front end via a front end processor, which communicates it back to the front end. I know it's very confusing. and that essentially is what the back end is doing. It's doing all of that work behind the scenes. And then banking examples are another example. So like if you think about like making a transfer in your online banking system, whether it's desktop or an app, I mean, the back end in the system is basically the Federal Reserve, the check clearing infrastructure of the Federal Reserve, or the SWIFT network, or any of the banking networks, and that essentially is the back end of what you're dealing with as a client of the online banking app, using it as a computer user, initiating the transfer that is then routed through the system by all of these back-end processors. Okay, front-end processors. We talked a little about this already, but I'll just go over it shortly. And the first thing I want to do is mention my favorite company in the world, Rockwell Automation. well, maybe not favorite company, but one of its. I'm in Milwaukee, Wisconsin right now, and Rockwell Automation is a major employer here. It used to be named Allen Bradley, and a friend of mine in elementary school worked for Rockwell as an engineer. Um, and Rockwell had this thing called ControlNet, or Ethernet. I think Ethernet is actually closer to what a front-end processor actually is than ControlNet, technically. So Ethernet basically it's a communication protocol um, between machines and automation, between machines on the factory floor and the computers that control the machines. So Ethernet is the communication protocol that connects the computers that coordinate the machines. It's pretty cool software, and there's documentation that is somewhat public. But I believe that the actual specification of the protocol is proprietary. The front end processor is responsible for communication, and it manages how data moves between systems, and it acts as an intermediary between users and the devices and servers that they use. And kind of a way to think about it is like a translator. So a translator translates languages from one to another, and the front end translates messages from the machines in Ethernet to messages to the computers, and the messages from the computers are sent back to the machines, translated using that common protocol of Ethernet. In the case of the Allen Bradley product that they developed. So, I mean, protocols are probably the best way to think about these things, and front-end processors are the hardware scaffolding upon which software protocols are based. I think that's the clearest way of defining what a front-end processor is. So things like network interface cards, they're in your computer, and they are the hardware that supports TCP/IP, and they are built to accommodate that protocol. They are optimized for that protocol, just as Allen Bradley's Ethernet is optimized for that particular communication between an IoT device on the factory floor and their computer terminals, which are running proprietary software that are designed specifically for that manufacturing operation. And the software developed for the manufacturing operation is actually developed by Rockwell does that, but I'm sure that they license Ethernet to other companies who are developing software and paying a royalty to Allen Bradley for the use of the Ethernet protocol to develop their software with. So there is definitely a licensing agreement in place for all of the software companies that are designing software based on the Allen Bradley protocol. But the key idea here with front end versus back end processors is that there's a separation of responsibilities. So communication tasks, front end processor, and then computation and logic, back end processor. And this division of labor improves efficiency because each component specializes on what it does best, and especially what the underlying hardware is designed to support. So the underlying hardware for back-end processors is different than the underlying hardware of front-end processors. They fit together hand in glove. So, I mean, in addition to the specialization and division of labor, there is also a performance benefit because if communication and processing were handled by the same component, the system would be overloaded. So by offloading communication to the front end, the back end can perform more smoothly and scale more efficiently. Okay, so file sharing experience. So I just used Google Drive to share a document this morning. And it is invaluable for being able to share a document that you can revise without changing anything about what you sent to the other person. So I'll send a URL in the form of a file path or a path to my Google Drive document, and I'll send that URL to the recipient. And then if I want to go in and change something, I don't have to upload another file and send it as an attachment to the person saying, oops, sorry, I just realized I have to do this. No, instead, my revision can take place within the Google Productivity Suite. And I just go in there, make the change, and nothing happens except that the change is made and the URL remains the same. And it is invaluable for collaboration because all of a sudden you're not swapping versions of documents of the actual documents that have been downloaded and which version is which and are we sure we're working off the same version? No, you have one single point of truth that everybody can work off of that is updated in real time, and it is just it's invaluable. File sharing is invaluable, and I would strongly encourage you to use it if you don't already use it. Um, I think attaching files to emails is certainly on the decline and should be, given the access we have to this cloud computing. And it is also much more efficient than sending attachments through the mail system. It is much more efficient with regard to bandwidth to have something sit on a central server and be accessed when it needs to be, rather than be routed through the system from Google Drive through the mail system to your recipient, when it could just remain on Google Drive in the meantime. And maybe the recipient never opens the file, in which case the bandwidth isn't lost. So it's a no-brainer. File sharing is absolutely something that um, that should be more widespread than it already is in business, which and elsewhere, academia, anywhere. It is something that really deserves to be um, that deserves to be um, taken up to a much greater extent than it already is. Okay, we're nearing the end. Client-side scripting. So now we've looked at how systems share data and communicate. And the next concept to understand is client-side scripting. So this is what happens in the user's browser rather than on the server. And um, this this essentially is what I was talking about with JavaScript, where certain tasks are handled locally and on the user's device, instead of sending everything to the server and waiting for a response. So the browser can process some things immediately, and this makes applications feel faster and more responsive. So, like, the best example is form validation in my mind. So if the browser can say, oh, you didn't insert the @ sign on your email address and catch it before it goes to the server, that is saving a round trip in terms of bandwidth and processing um, from ever being executed. So it is important that client-side scripting be implemented in order to save these precious computing resources that we rely on. And then another example is user interface elements. So things like drop-down menus, animations, and this is it's a matter of performance and resource conservation for the system as a whole. But also it makes websites feel more dynamic and engaging. So there's also an experiential benefit to it, in addition to the resource conservation that I talked about earlier. And then another example of client-side scripting is when a page only partially loads or partially reloads. So, I mean, if you think about like, you can separate the page into containers and have only a container load. So if you have a notification on Facebook that you receive, your whole Facebook page doesn't reload when that notification comes through. Only the portion of the page that concerns that notification reloads, and that saves a lot of processing power and a lot of resources. So basically, things like that reduce the workload on the server and also reduce the amount of traffic that has to flow through the internet. And web traffic is not costless. I mean, there's a transmission cost associated with that. And in addition to that, server processing costs, those two can be substantial, especially when you're talking long distances traveled on the internet. That transmission cost can become very, very high. And the processing cost is similar, whether it's on the server or on the client. So the main gain is in the transmission cost. Okay, so the final topic I'd like to cover is server-side frameworks and languages. So there are four major ones: .NET, Ruby on Rails, which is usually just shortened to Ruby, Python, and then PHP. And these are the tools that developers use to build the server side of the systems. And they provide structured ways to create applications that, as we know from our discussion on backend processors, handle data, logic, and user interactions. So the user interactions that are not handled by client-side scripting. So basically, each of these frameworks is a toolkit. So developers choose different frameworks or toolkits depending on what type of application they're building. And I'll just run through these real quickly. So .NET is usually used in enterprise. And .NET is a Microsoft product, and it provides built-in built-in support for security, database integration, and it also helps with scalability. So, I mean, a company might use it for an HRIS, a human resource information system, or even something like OLTP, online transaction processing. And then another example of a server-side framework is Ruby, as I said, and Ruby is focused on rapid development and focus on convention over configuration. So, I mean, it's a very kind of like cookie cutter approach that allows products to be launched quickly. Python is another option with two different flavors, Django and Flask. And Django is used for larger applications, whereas Flask is used for microservices primarily and APIs. PHP is used to build dynamic websites. And the best known example of this is WordPress, which covers like 30% of the internet, I think. Is maybe it's 30% of blogs. 30% of the internet seems ridiculous. I think it's 30% of blogs, which is still a large amount of the internet. PHP allows websites to generate content dynamically based on user input or database information. So the commonality between all these frameworks is that they help developers build the backend systems that power applications. And so that brings us to the end of this presentation, and thanks for staying with me. And I just want to kind of call out a few topics as takeaways. The main balancing act in establishing a client server system is between efficiency, control, and reliability. And control here is meant to be a synonym for security. So you want the server to be secure. You want the processing to be efficient, and you want the server not to be. You want the clients not to experience outages of the server. So centralized servers make it easier to manage data and security, but if redundancy and failovers are not provided, you can't have those outages that we talked about. And then the other kind of key takeaway is that communication between client and server is really kind of the key topic here. And how do you structure that communication in a way that allows for clients to have the access they need and servers to have the security that they need to maintain? So from Golda Meir Library at the University of Wisconsin-Milwaukee, I am signing off. Thanks for being with me, and I hope you have a good rest of your day. Bye.